My name is Jeannie Rasmussen, and I am representing South Dakota with Model for Sustainably Powered Ultraviolet Irradiation Water Purification System. My objective was to develop an adaptable UV irradiation purification unit that is both sustainably powered and operable independent of the electrical grid. Now, UV light is especially attractive for water treatment, particularly because of its high energy efficiency. But as I was researching, I found that few designs exist that take advantage of UV light while incorporating a sustainable power source to limit environmental impact. Considering the high rates of waterborne illnesses in certain areas of the world, a model for a system that doesn't require grid access would be conducive to safer water on a global scale. As a refinement of a project begun last year, I replaced a solar power source with a hand crank generator, both to increase the usability and to corroborate the feasibility of yet another sustainable power source option. A second change replaced the quartz glass sleeve that protected the bulb from water exposure with a fluoroplastic envelope, which is both cheaper and more manipulable in terms of design applications. Now, before I was able to technically begin designing the model, I tested the UV transmittance properties of the fluoroplastic film I received. Because it was not pure FEP, it wouldn't transmit the germicidal rays effectively. The test used a spectrometer to detect whether light rays at 254 nanometers, which is the wavelength my bulb emits, arrived outside of the sheath, and the data shows that it did so effectively. It was also necessary to calculate the time needed to disinfect water at a certain distance from the bulb to ensure effectiveness. After approximating some attenuation figures, I used the inverse square law of light and the UV fluence formula to determine that the bulb theoretically needs 262 seconds to disinfect water about 6.5 centimeters away. Now, once preliminary tests were out of the way, I was able to construct the device. As you can see here, the main cylinder is aluminum. The bottom half is where the water is housed while it's disinfected, and the top half here holds the electrical components as well as the charcoal prefilter. In the electrical compartment, energy flows from the generator to the battery where it is stored before it passes through a converter, an inverter, and finally to the UV bulb. Water is poured in through the macrofilter and then flows into the water chamber where it is disinfected with the UV bulb that protrudes through a hole in the electrical compartment. The bulb is protected from water exposure by the FEP sheath. So after the model was constructed, I conducted some testing on the charcoal filter to demonstrate its pre-filtering capacity. Pre-filter is actually critical in terms of UVGI applications because large particles can shield bacteria from UV exposure, resulting in a residual concentration of bacteria in the treated product. In this test, I added some soil to tap water and ran it through the filter, and the results show greatly reduced turbidity in the filtrate. Now, at this point, I can pretty confidently say that I met my engineering objective. This device here functions as a model for a sustainably powered UV purification system that is usable off the electrical grid. Now, of course, since this device was constructed as a model and not a marketable device, further research could be conducted to consider specific pragmatic applications and to optimize the design for cost effectiveness and efficiency. A large-scale adaptation of this model could potentially serve entire communities and reduce waterborne illnesses. The number is 400 kids under the age of 5 that die from waterborne diarrheal diseases every hour, and the implementation of a reliable, cost-effective water purification system has the potential to reduce that number as well as minimize the environmental impacts of its use.